Hi, my name's Ian Hothi. I'm a third-year PhD student at Imperial College in London, and today I'll be presenting work from my recently accepted paper of comparing foreground removal techniques for the recovery of the LOFAR EOR 21 centimeter power spectrum. I'll first start off going over various foreground mitigation techniques that one can use in order to recover the 21 centimeter signal. Now, these fall into two schools. The first is foreground avoidance. Now, on the left here, we have the cylindrical power spectrum, which is the power spectrum binned along the line of sight and angular domain. And due to the chromatic nature of the instrument, the fact that its response changes with frequency, we end up getting what's known as a foreground wedge, below which we get all of the instrumental effects, as well as the intrinsic foreground, such as galactic synchrotron emission. The corollary of having the foreground wedge is that there should be certain K modes in our power spectrum that should be free of foreground contamination and should just be the 21 centimeter signal and noise, and we call this the EOR window. Studies that focus on avoidance tend to use the modes in the EOR window for their analysis. Foreground removal looks to model the foreground and subtract it from our data. These fall into two schools. The first is parametric methods, where you assume the form of the foregrounds, and non-parametric methods, where you don't assume the form of the foregrounds, and you use the data itself to model the foregrounds. For the purpose of this paper, we'll be using foreground removal. The first two of which are known as blind source separation techniques, which are FastIC and GMCA. So the general equation that they use is this. And so the observed signal is made up of the foreground model. Now the foreground model is decomposed by GMCA and FastIC into a mixing matrix and source model, which we look to optimize. In an ideal world, the source model would be a column matrix where each row is a different foreground, and the mixing matrix would be the identity matrix. However, in reality, these deviate away, and the source model becomes a mixture of the different foregrounds, and the mixing matrix deviates away from the identity. FastICA finds this through statistical independence, whilst GMCA uses morphological independence. Once we find our foreground model, we can subtract it from the observed signal and get the Gaussian noise, which should contain the 21 centimeter signal and noise of the instrument. The main hyperparameter of these techniques is the number of components with which you wish to model the foregrounds. An example of a source model is this. Here we've modeled the foregrounds with 3 components, and we can see that one of the components in the center looks like galactic synchrotron emission, which makes sense because it's the most dominant foreground emission, so you'd expect it to get its own component. The third technique we'll be using is Gaussian processes, so Gaussian process regression. A Gaussian process is a probability distribution over functions. Much like a normal Gaussian, it's fully defined by its mean and covariance. The covariance is represented by a kernel. This is an example of a kernel. The type of function you get from a kernel, we can see the type of function on the right, is fully defined by this new parameter here. And the main hyperparameter of your kernel is the coherency length. So for example, the foregrounds will be fairly coherent along the frequency direction, roughly 50 to 100 megahertz, whereas the 21 centimeter signal isn't very coherent. And so it has a coherency length of the order of a megahertz. Now the overall kernel of the observed signal can be decomposed into the different foregrounds of its constituents, right? Because we've just mentioned that the coherency length changes. And because the coherency length changes, we can model each of them with different kernels. And we can give uniform price to the coherency length of each of these kernels and use Bayesian optimizations to optimize the kernels. Now, GPR is what is currently used by LOFAR to get its upper limits. GMCA has been used in the past by Patel et al. 2017. Now, the main goal of this paper is to compare the 3 foreground removal techniques to see which is best. So the first thing and the most obvious thing to do would be to apply it to the most recent data. And we find that all 3 techniques, with GMCA and FastIC modeling the foregrounds with 6 components, recover the most recent LOFAR upper limit here. And so for the lowest of K modes, all 3 techniques perform pretty similarly, right? We've used our own application of GPR almost as a sanity check to make sure we're doing everything correctly. And so all 3 techniques and the lowest of K modes in a power spectrum perform pretty similarly. And then at around a K value of 0.1, GMCA and FastSA begin to deviate away from the result of GPR. And now the motive of this paper is to find out why or what is causing the degradation of performance of GMCA and FastSA with K, as GPR clearly stays pretty close to the noise. And so the obvious thing might be instrumental effects. And so we simulate the foreground. So we simulate the foreground using Yellow et al. 2008 outline, and the Cosmos signal using 21 centimeter fast. We know the fact that it was a 10-night observation, so we can use OSCAR, which is an interferometric simulation, to apply instrumental effects. And we have three cases here. In case one, we do a normal 10-night observation. In case two, we do a 10-night observation with kind of LOFAR specification, of course, but we don't apply the primary beam. And in case three, like I mentioned, the instrument is chromatic and its response changes with frequency. So we take the lowest frequencies PSF and apply it to the entire bandwidth. And this effectively smooths over the bandwidth. And thus, we remove the mode mixing. So case one is a normal observation with obviously the LOFAR specifications pointing to OSCAR for 10 nights. The same is true for case two, but we remove the primary beam. And with case three, we remove the mode mixing. We show GMCA here because GMCA and FastSA perform pretty similarly. And we see that for case one and case two, there isn't a significant difference between them. And that makes sense because we cut our field of view to be within the primary beam. So it has very limited impact. But interestingly for GMCA, in case three, whilst we get a deeper power spectrum, which is to be expected because we've removed a source of power here being this mode mixing, for the highest of K modes, whereas 3 in the normal case was sufficient to model the data, here 3 is too many and we begin to see overfitting. But there isn't a clear reasoning yet as to a single effect that's causing the degradation with K, because obviously here we see an improvement and a slightly deeper power spectrum. And so we try other things. We for example, increase the bandwidth, because normally GMCA and FastSA are used on hundreds of megahertz of bandwidth. We've given it 10. So we increase the bandwidth to 30 and 50 megahertz. And we do see an improvement with GMCA and FastSA as we increase the bandwidth, but the improvements across all K scales. But we see hints of what the problem might be. One might note that the simulated case here looks a lot better than that for the observed data, right? We only need 3 components and we really get below the noise. And the second thing is, again, when we remove mode mixing, we start to get overfitting at the highest of Ks. And so what we know is GMCA and FastSA, being blind source separation techniques, are scale independent. If I say to GMCA, find 3 components, it will find 3 components at every single scale. Now, Andrea Effinger showed last year that RFI flagging can increase power. So it introduces excess power into our power spectrum and into our data. And this increases with K. So we thought, okay, let's try to emulate this effect. So we flag our data. We flag roughly 1/3 of our data, and we apply FastSA to this. And we can see that when we have the unflagged case, when we have the unflagged case, as we see here, we perform pretty close to the noise. But the moment we start introducing flagging, we start to see excess power, and 3 components at the highest of K is no longer sufficient to model the foregrounds. And so what we can conclude now is that what's going on here is the fact that all of the instrumental effects and even the RFI flagging that Effinger et al. 2019 looked to mitigate increase the excess power at the highest of Ks. And so when I say to GMCA and FastSA, find 6 components, it finds 6 components at every single scale. And now this might be sufficient for the lowest of k-scales. As we get to the highest of k-scales, when all of these different effects, such as the mode mixing, such as the RFI flagging, increase the number of components, 6 components is no longer sufficient to model the foreground. And so what we end up getting is underfitting. And so we're no longer sufficiently modeling our foregrounds at the highest of k's. And hence we get this seemingly degradation in performance. And we can see this here again. So this is the cylindrical power spectrum ratio, where we've taken the cylindrical power spectrum of the GPR result and the fast ICA result and taken the ratio. And we can kind of see at kind of high K values, we can see an increase in power showing this degradation, this increase in excess power. But interestingly, actually, is on the lowest of K scales, we begin to see overfitting. So in fact, even 6 components, whereas 6 components on the highest of K is insufficient to model foregrounds, what we're actually seeing is on the lowest of K, 6 components is too many to model the foregrounds. And so what this shows is we need a blind source separation technique that can model the foregrounds with different number of components on each scales. So to conclude, with the 3 techniques, we recover the most recent LOFAR upper limit, with the blind source separation techniques having the performances degrade with K. We find that no single instrumental effect is causing this, but in fact, it's caused by the fact that the blind source separation techniques are scale independent. We conclude that GPR, both for its performance on 10 megahertz, is the most optimal technique. However, this begs a few questions. The first is, are we performing foreground removal with the blind source separation techniques in the most optimal way? We've given it 10 megahertz of bandwidth when it normally performs on hundreds of megahertz of bandwidth. And finally, we should move towards a slightly more scale independent approach, right? I've shown that the number of components you need to model the foregrounds changes with your K scales. And so even 6 components was too many on the lowest of K scales, but insufficient at the highest of K. So we need a technique that can model different number of components at different scales. And we see that the issue of not forward modeling, we see the issue of not fully modeling and simulating our data, right? In an ideal world, we might apply Oscar and simulate our foregrounds, but we're not capturing all of the kind of calibration the calibration errors that one would expect, nor the excess power that arises from foreground, from RFI flagging. And so thank you. Just